All right, welcome back to Cache. We ended our first part right here with permuting the order of the three for loops in a matrix multiply and what a huge difference that can make. But now let's go on to some cache architectures. So the way caches are put together now, they're called n-way set associative. Um, I've colored them here. If I if I was naming this, I would call this two-way set associative. Basically, all the cache lines, think of the cache lines in memory as having numbers and colors. So here is 4 cache lines, and we've set this up to be, well, it's two-way set associative, and we've got 4 different places to put cache values. Cache does not work by, okay, I need a cache line. I can put this anywhere in the cache memory. Apparently, they found out that that didn't work well. So what they do is they have certain reserved spots. Hey, like you buying a reserved seat at a movie theater. It prevents chaos. So anything that's a red block, notice we go red, orange, yellow, green, back to red. Cache lines have numbers on them. So here's the first cache line, the second, the third, and so on. But because we're doing 4 groups here, then the fifth one is the same group as 0 is. Okay. So if we say two-way set associative, it means we have 2 cache lines for every group. Okay, and those groups are called sets. So we have 4 sets and 2 cache lines per set. Okay, so if I pull something from this block here, that cache line is going to go in either this place or this place in cache memory. Can't go over here, can't go here, can't go here because, well, it's a red block. Now, what if there's already things in cache there? Well, the least recently used one will get kicked out and a new one will get brought in. Okay, so that's how cache architectures work, and this is under control of the hardware. Now, how does this work arithmetically? You're not responsible for this, but if you're interested, here's how the numbers work. If you're not interested, just put your hands over your ears. So in our diagram here, we have 8 total cache lines. That's a ridiculously small number, of course, because if you take 8 times 64 bytes, you get 512 bytes, which is a really small size of a cache, but fits on the slide. Okay, so we have 8 cache lines here. It's two-way, meaning each color gets 2, which means there's 4 cache sets, which means we're going to divide memory up into a group of 4, then the same group of 4, then the same group of 4, and so on. All right, so let's say we have a memory address we want to go get. There are 64 bytes in a cache line. We divide that memory address by 64, and that tells us which memory cache line we're in. Okay, and because we have 4 of these sets, we do a modulo mod, which will give us back 0, 1, 2, or 3. And that'll tell us, well, this address in memory is going to go in one of the sets. You said 0, 1, 2, or 3. That tells us now the set number. If there's something already there, then we're going to pick the least recently used one, kick it out of cache, and bring this cache line in. Now, we're bringing in 64. And cache lines in memory, you can tell what a cache line in memory starts because the bottom 6 bits in the address are all zeros. Okay, cache lines start whenever the bottom 60 or 6 bits of the memory address is all zeros. Okay, so if we just do a mod of the memory address with 64, that tells us how far down the cache line this is. Okay, so two pieces of information are needed in the CPU chip. Where is the cache line that contained that memory value? And how far down the cache line is the memory value that I wanted? And those two pieces of information tell the hardware how to go get this. Let's use an example. So let's say the memory address where we want to go fetch a floating point number is at address 1234. Well, if we divide by 64, that'll tell us it's in cache line number 19. If we mod cache 19 with 4, we find that 0, 1, 2, 3. In every group of 4, well, cache line 19 is in block number 3, means we're going to bring this whole cache line in, and it's going to end up in one of these two places right here. And then if we mod that with, we find out how far down we are in the cache line. So actually, memory address 1234 will live either here or here in cache. And that's where the hardware will go look for it. Okay, but here's the other trick. Now along comes multi-core. And well, wait, when we had one core, there was just a one L1 cache, one L2 cache, one L3 cache. But now that we have multiple cores, how do we manage that? Well, the answer is what they decided to do. And again, I think this is something that has been so consistent over the years, there must be a special reason for it. But every core gets its own L2 cache. Okay, that way it can do caching against itself, and it can run faster that way. Okay, and how does it manage this? Well, each core's L2 cache has 4 states, and it's called MESI, not messy. That's something else. It's called MESI, as if that was a Z. And the MESIs stand for modified, exclusive, shared, invalid. And so every cache line in a core's L2 cache is labeled as one of these. So let me run an example. So let's say that core A, we're only going to do 2 cores here. Core A reads a value out of memory. It's not in cache already, so it goes to memory, brings it back, sticks it into core A's cache. And because it's the only one using that cache line right now, that cache line is tagged as exclusive, the E in MESI. Okay, but the cores are running independently, and core B decides to read a value from the same cache line. Maybe not the same variable, but maybe a couple variables past it, but it's in the same cache line. So now that cache line is actually in the CPU chip twice, once for core A, once for core B. But because both cores are reading from it, there's no problem. But it changes the state from exclusive to shared and shared. Okay? So now the hardware knows that that one cache line is in 2 places on the CPU chip, and it's being shared between or its access is being shared. But right now the cores are just reading from it, and so there's no problem. All right, core B decides to go rogue and write a value in the cache line. Okay, for all we know, core A is just about to read that same variable. But if core A reads that same variable, it has the old value for that variable in its cache. It's going to get the wrong answer because B has already changed it. Okay, so at that moment, when B writes into that cache line, core A's version of the cache line gets a status change. It's changed to invalid, meaning if you read from this again, your chances are you're going to get a wrong number somewhere because somebody has already changed it, but your cache line doesn't know that yet. okay? And B status changes to modified. And what happens now is that the hardware says, I need to change this. I need to update Core A's version of the cache line. And so what it does is it takes Core B's cache line, flushes it out to main memory, that is, updates it to main memory, and then brings the whole thing back again into Core A. So Core A's cache line is now correct. Well, that's really time consuming, right? Okay, this is this thing called false sharing. And this is how it happens. And it's perfectly innocent. It's just when you're using two variables that are in the same cache line, the moment one core writes that variable, that causes the hardware to invalidate the other core's version of the cache line. And then it has to update it so that it can be used. Okay, so note that false sharing is not creating incorrect results. In fact, it's guaranteeing correct results because it's keeping every cache line in the L2 caches up to date. So yes, we want it to do that. However, we wish it wouldn't. We wish it wouldn't create such a performance hit. Okay, yeah, if you do a state diagram, here's what it would look like. Okay, let's work a problem. So what I did is I created a struct, and all the struct does is it's got one floating point value in it, and I've got four of those. Okay, so it's an array of structs, and each struct has one floating point value. I'm going to set the threads in the thread team to 4. I'm going to go pragma OMP parallel 4, and I'm going to do this. And so this is here just to create work to do. But here we're going through, basically, by doing this, we know that 4 threads are going to get assigned to first for thread 0 to I equals 0, thread 1 to I equals 1, thread 2 to I equals 2, thread 3 to I equals 3. Okay, so by using the same number here and here, we know that each for loop pass is going to end up on its own core. And here we're just doing a bunch of work. Okay, so this struct, the array values, array 0, well, that's its float value. Array 1, that's its float value. Array 2, this is its and this is its. Okay, and this whole set of boxes, 16 floats, that's 64 bytes. This is one cache line. All right, now here's what we're going to do. We're going to stick another variable in here, and we're going to change the value of numpad. When numpad is 0, meaning I have no elements in my array, then essentially we're getting this. Okay, it's as if that pad array isn't there at all. And that actually works. If you dimension an array at 0, it will take it out of your code. Okay, so when numpad is 0, we're going to get this. They're going to be back to back in the same cache line. So let's say numpad equals 3. Well, there's going to be a gap of 3. So the first value, a gap of 3, the next value, a gap of 3, and so on. So the green boxes are where the gap or where the values are, and the white boxes are the gap. Okay. When I ran this with 1, 2, or 4 threads, this is what I got for performance. And what I did is I normalized everything to one thread. So one thread is a speed up of 1.0. Okay. When I use 2 threads, well, look what I got. I got less performance. Like, how can that be? So far in your projects, when you up the number of threads, cores, then you get better performance. But here we're getting worse. And then it gets worse. And then it gets worse. Now, eventually it gets better. So we need to figure out, why is this happening? Here we go. When numpad is equal to 0, the 4 values are right here. But because the four values are right here, all four cores have this cache line. So the moment one core tries to write to the cache line, see, here's the code. The moment one core tries to write to the cache line, it invalidates the other three versions of this cache line. And so for them to use it, well, things have to go out to memory. They have to get brought back. Big time commitment. Okay, and that's with numpad equal to 0, which puts these values on the same cache line. Let's try numpad equal to 1. And this is numpad equal to 1. And I'm just going to move this black bar over as we go. Numpad equal to 2, basically no difference. Numpad equal to 3. Numpad equal to 4. The values are still on the same cache line. They are still invalidating that cache line in the other core's L2 cache. Now let's change numpad to 5. That moves one value to the next cache line. See, we're putting all this padding. We're padding 5. Value 5 pads, value 5 pads, and that forces this one to the other cache line. And now look what's happened here. What's happened there is that our performance has suddenly gotten better, right? Yeah, our performance has suddenly gotten better. Both the 2-thread and the 4-thread curves have bumped up. They're still no better than no threading at all, what, one core, but they've bumped up from what they were. So that's a good sign. And why did they bump up? Because you can read and write this value all day, and it won't invalidate this cache line. It's a different cache line. But if you read or write, or if you write this one, that invalidates core 0 and core 2's version of that cache line. All right, here we go again. Let's change numpad to 6, numpad to 7. Well, now, well, yeah, this one and this one will invalidate each other's cache line. This one and this one will invalidate each other's cache line. But a moment ago, we had 3 of them invalidating each other's, and now we only have 2 at a time. Okay, so we're going to get less invalidation happening, and sure enough, our performance jumps again. Okay, like this. Now we'll do numpad equals 8, numpad equals 9, numpad equals 10. Well, now we have only one core using this cache line, only one core using this cache line. We still have 2 using these, but we have now bumped up here, okay, with the 4 threads. Let's play more numpad games. 11, 12, 13, 14, 15. 15 pads results in this. Okay, on the 15th, the 4th thread is finally running at its potential because nobody is invalidating each other's cache lines anymore. Okay, and so you're thinking, yes, but putting 15 pads in is a real waste of memory. And yes, it is. There's no question about that. But check out the effect of 4 threads. A moment ago, we were down here, like half the performance of no threading at all, bumped up to almost 4 times the performance of no threading. So that's quite a difference. I'm not sure people put 15 pads in there, because typically you don't have just one float in your struct. But if you've got a bunch of things in your struct, people very much will pad it to make it fit in one cache line so that the next struct begins on a brand new cache line. Because again, you can see the performance you get. So this is the heartbreak of false sharing. You think you've done everything correctly, and you have done everything correctly. But because of the way cache works, you're getting this, this horrible performance loss. And that's why it's called false sharing. You think you're sharing, you think you're doing multi-core, and well, you are, but it's not working out the way you thought it would. There's got to be another way to fix this. So I call this fix number one, adding the padding to force values onto their own cache lines. Another one is to remember that local variables are kept on, well, different stacks depending on which thread you are. And so here's another way to do it. What we did a moment ago is we said array I.value equals array I.value plus something. So we were reading and writing array I.value. But since all we're doing is adding into it, don't add into the global variable, add into a local temporary variable. So temp equals temp plus. That's the other fix, because now we are not writing into global memory, we're writing into stack memory. And so we're not invalidating a global memory cache. And if we do that, well, there's no pads going on. And so for fix number two, this is the 4-thread performance, and it matches the numpad equals 15, fix one performance. For 2 threads, this is the fix number two performance, and it matches, well, what happened when thread two reached its real potential. And then fix number two's 1-thread performance, well, that's the same as what it was before. Okay, so yeah, there's typically 2 fixes for doing this. One involves padding out to be an even cache line, and the other involves trying not to write out to global memory, at least not so often. Now, with that kind of a discussion, you can probably discern that there actually is an advantage to starting your data structures on perfect cache line boundaries. See, let's say I had a 64 byte, I have 16 floats. If they straddle 2 cache lines, then I'm going to be playing cache, 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 cache games. But if those 16 floats are in one cache line, then I can do anything I want, and it'll just use cache memory for the operations. So how do you do that? Well, if you could peek at memory, anywhere in memory you see an address where the bottom 6 bits are all zeros, that tells you that that's the start of the cache line. So here's the trick. If we want to do that, so we're going to say, I want array size, array of floats, or an array of structs, but the number of structs is array size. Okay, normally we would do this, and I'm going to do it in C. We're going to malloc, and the number of bytes we want is array size times the size of the structure, number of bytes in the structure. Okay, and I assign it to P, and I assign that to array, and then I can use that array variable just like this, just like we did. Okay, but this doesn't necessarily start on a cache line boundary. To make it start on a cache line boundary, what we do is we still malloc this array size times the number of bytes in the struct, but we allocate a whole nother cache line. Okay, a whole cache line that we don't need. But then we do this. We take that address and we AND it with 6 bits. Okay, 3 is 2 ones, F is 4 ones, that's 6 bits. And what that's telling us is where in that over allocated array does a cache line start. And so what we're going to do is we're going to set this value of array equal to where the cache line starts. And now we can still use the name array just like we did before, because array is not pointing to the beginning of what we malloced. It's pointing to some amount down what we malloced, but at the start of the cache line. That's why we over allocated it. Okay, Now, the only trick to this is when you want to get rid of this, you don't do a free on array because array isn't what you malloc. P is what you malloc, so you say free P. Anyway, that's the trick to this. And so again, overall, cache is a great thing for every programmer to know something about, but that false sharing is so insidious. Think you've done everything right, and your performance just turns to mud. Um, you don't want to, you don't want to do that. It is just an insidious problem. This I've heard also makes a good interview question. Okay, in a job interview, and someone might say, "Hey, explain false sharing to me." So this is definitely something to know something about.